Okay, we are going to be learning the rules for naming a covalent compound. So, refreshing ourselves on what a covalent compound is, it is when you have two bonding atoms between two nonmetals. So a covalent compound is only between nonmetals, as you can see here on the periodic table. Properties of a covalent compound include the fact that they share electrons. If you recall, ionic compounds involve the transfer of electrons from one element to another, whereas a covalent compound, they share them between the two of them. They also have a definite and predictable shape. They tend to have low melting and boiling points. They are relatively soft solids, and they can exist as solids, liquids, or gases. So if you compare the ionic versus the covalent, you can see that ionics form what are called ions. These are positively or negatively charged elements or molecules or compounds, whereas a covalent forms a non-charged molecule. Ionics can be molten salts. They're conductive, they transfer electrons, and they have a high melting point. Whereas covalents share electrons, they are not very conductive of electricity and have a low melting point. They also have a higher electronegativity, and they both share the fact that they use valence electrons for bonding. Now, naming covalent compounds is very easy. For a binary covalent compound, we use prefixes to represent the number of atoms in an element, and then the name ends in "ide." So you look at the subscripts. So if the subscript is 1, you call it mono. If it's 2, di, 3, tri, 4, tetra, 5, penta, 6, hexa, 7, hepta, 8, octa, 9, nona, or nona, and 10, deca. For example, if you have CO, you call it carbon monoxide. Now, we don't say monocarbon because if the first element only has 1, you don't put a prefix in front of it. So CO2 is carbon dioxide. Nitrogen, NO is nitrogen monoxide. And P2O3 is diphosphorus trioxide. Now, because there is 2 phosphorus, we do put a prefix in front of that one. You just don't put a prefix if the first element only has 1. So, when we are drawing the Lewis dot structures for a covalent compound, it's important to determine the number of bonds in a covalent compound. Now, this is very important. You can't just ignore this step. This is something different that we didn't do with ionic compounds. So to determine the number of bonds that has to exist in a molecule, you use the following formula. And it's N minus A, and that should be over 2. And the answer that you get there will tell you the number of bonds you should have. Now in this formula, N is the number of needed electrons. And for all elements, it is 8. Okay, except for hydrogen, which only has 2. A is the number of available electrons, which is the number of valence electrons. Valence electrons are all an element has, and N is what it needs, which in most cases it's going to be 8. So, just to refresh ourselves on valence electrons, they are the number of electrons that orbit the outermost orbital of an atom. These are the electrons that are involved in bonding, and we determine them by looking at the group they belong to on the periodic table. So all the noble gases have 8, the halogens have 7, 6, 5, 4, 3, and so on. So, to determine the Lewis dot structure, you follow these steps. The first step is to determine the number of bonds needed with the formula we just talked about. Number 2, you draw a skeleton structure. So the least electronegative element is the central atom. So we just learned about periodic trends. So the one that is least electronegative, so look at your trends, that's going to be the one that's going to be in the center, and then all the other ones are going to go around it. You connect the atoms with the number of bonds that you determined in step 1. Then you finish by making sure all the atoms in the structure have an octet of electrons, so they all need to have 8. So you might have to go back and finish off with the dots if you remember the way we did it with the ionic compounds. And remember, if the structure has a positive charge, it has fewer available electrons, and if it has a negative charge, it has more available electrons. So this will affect the step 1, the number of bonds that you needed to, the numbers that you used in the formula to determine the number of bonds, so that's going to change. Okay, so we're going to do an example problem here. Okay, so we're doing CO2. Okay, so our formula is N minus A over 2. N being how many they need. So carbon and oxygen both need 8. So I'm gonna add them up. Okay. So I've got carbon and each oxygen. Okay, so there's 1 carbon and 2 oxygens. Okay, 8 plus 8 plus 8 is a total of 24. Okay, and that's our N. Our A is how many they actually have. So what's their valence electron? For carbon is 4. For oxygen it's 6. And then the other oxygen is 6. So 6 plus 6 is 12. Plus 4 is 16. Okay, so now we go 24 minus 16 divided by 2. No, let me see. Sorry, that's A. Okay, so that gives you 8 over 2, which is 4. So that is the number of bonds that has to be in our molecule. Okay, so we're going to put the least electronegative one in the middle, which is carbon. So we're going to put oxygen on either side of it. Okay, so we have 4 bonds, so I've got to draw 1, 2, 3, 4. Okay, the last thing I got to do is make sure that everybody has 8 electrons. So we know each of those lines represent 2 electrons. So for the first oxygen, I've got 1, 2, 3, 4. And I'm going to go 5, 6, 7, 8. Same thing to the other oxygen. Carbon already has 8 electrons around it, with each of those lines being 2 electrons. So 2, 4, 6, 8. So this is the electron dot for CO2. Okay, so a few rules that need to be mentioned when it comes to carbon. Carbon follows all the rules previously discussed, but has a few unique properties that you need to remember. Carbon is always the central atom in its compounds, and it tends to undergo bonding to itself. This means that carbon likes to bond to another carbon. So if you've got more than one carbon, they're gonna bond right next to each other, and this is called catenation. Also, carbon always has 4 bonds, so you're never going to put those lone electron pairs around carbon. It's always going to form at least 4 bonds. Anytime you have a choice for a skeleton structure, always go for the most symmetrical option. And this is just a good rule of thumb with anything, but especially with carbon. Okay, so if we were doing the Lewis dot structure for these, so we'll just do one of them. You follow the same rules, the N minus A over 2. Okay, so each carbon wants 8. I've got 6 hydrogens, and each of them want 2. Because remember, hydrogen's small and it can't have 8. So, okay, so when you add these up together, you should get 28. Okay, now with that, and that is our N. For A, we take our valence electrons. We've got 2 carbons, and then again we've got 6 hydrogens. Each of them has 1 electron, so 6 times 1 is 6. 6 plus 4 plus 4 is 14. Okay, and that's A. So now we do 28 minus 14 divided by 2. Okay, so that gives us 14 over 2, which gives us a total of 7 bonds. Okay, so we know that carbon likes to bond to each other. So since we've got 2 carbons, I'm going to immediately put them together. Now, since I want to make it very symmetrical, I want to give each of them 3 carbon, or 3 hydrogens. So I'm going to put an H there. I'm going to put an H there. I'm going to give this guy, because I've got a total of 6 hydrogens. So I'm going to give 3 to each one of them, because I want it to be nice and symmetrical. So then I go back and add up whether or not I've got my 7 bonds I'm supposed to have. So I've got 1, 2, 3, 4, 5, 6, 7. So I do have 7 bonds. So that's my skeleton structure, my Lewis dot structure for C2H6. So the bond strength of a covalent bond depends on how much distance separates the nuclei. So the distance between 2 bonding nuclei, the position, is called the bond length. And in general, the more bonds between 2 atoms, the shorter the length will be. So a single bond will be the longest, whereas a triple bond would be the shortest. So by triple bond, for example, between 2 nitrogens, they have a triple bond. So that is a very short and strong bond, and it takes a lot of energy to break it. And so the stronger the bond, the higher you've got to boil it, and the higher temperature it takes to boil and to melt it. And the same thing, the weaker the bond, the lower the melting and boiling point.